Welcome PCS members and friends to our PCS IBS seminar. Today we have a pleasure of hosting Professor Tran Trung Luu from the University of Hong Kong. And our scientific host today is Zung, and I would ask Zung to introduce our speaker.
Okay, so hello everybody. I'm very pleased to introduce my old friend Tran Trung Luu. He is my high school friend. He goes to the undergraduate school with me at the Hanoi University of Science. After that, he also go to KAIST with me for his master in science. And after that, he moved to Max Planck Institute of Quantum Optics at Garching, Germany for his PhD under the supervision of Professor Ferenc Krauss, who won the Nobel Prize in Physics this year. After his PhD in 2016, he moved to ETH Zurich in Switzerland as an ETH postdoc fellow, and he currently is an assistant professor at the University of Hong Kong, China from 2019. And he actively engaged in the state-of-the-art research on ultra-fast laser and attosecond science. He contribute and play an important role in bringing the attosecond science to application. He used attosecond laser to probe the real-time dynamic of electron in material, and he received many honor and awards for his pioneer research. And let's welcome our speaker today. Thank you. Daily jobs.
Yeah, thank you very much, Thailand and Sun Dung for very kind introductions. And I hope everybody hear me properly. It's my great pleasure to be here to discuss with you some of the main concepts of attosecond science and their connections to the Nobel Prize in Physics in 2023. So as Sun Dung said, we did the master together in KAIST, so it's always a good feeling for me whenever I have a chance to visit Korea, Techen, or even virtually in this case. So I guess the talk can be a little bit informal, so please don't hesitate to interrupt me anytime. So first of all, I just want to remind you that you already know that in 1 month ago, the Royal Swedish Academy of Science already gave the Nobel Prize in Physics this year for 3 mainly experimentalists with the note that for experimental method to generate attosecond pulses of light for the study of electron dynamics in matter. So in the advanced introductions to the Nobel Prize, they did cite that about a century ago, when Heisenberg proposed one of the foundational papers for quantum mechanics, he was already anticipating that it is in principle impossible to observe the motions or the dynamics of the electrons. So fast forwards about a century nowadays, it has been shown and proven that we can actually probe, initiate, and track or follow the electronic dynamics in real time. So that was about 100 years ago that was thought to be impossible, but nowadays it has been shown by these 3 experimentalists and also collective efforts of so many other scientists for this works, creation of attosecond laser pulses and the use in probing the dynamics as well as properties of matter. So first of all, we would have to discuss what is attosecond science. So I just want to remind you, of course, many of you already know 1 attosecond is 10 to minus 18 of a second. So in order to understand the scale of the time scale we're talking about here, we have here videos. I think it is quite informative. So let's consider the speed of light. And if you consider the distance between moon and Earth, this is around 1 second of propagation of light. Now, if you divide that by around 1,000 times, then you will see that the distance from Rhine to Paris, you can cover this within just 1 millisecond. All right, so that is 1,000 times shorter than a second. Now, if you consider even a shorter distance like 300 meters, then that is the time scale of 1 microsecond we are talking here. That is already 1 million times faster than a second. And the time it takes for light to travel through, a baguette is only 1,000 times less than that. Right? So we are talking about 1,000 times, 1,000 times, 1,000 times less. And now we are already arriving at the order of a picosecond. So 10 to the minus 12 of a second. Incredible, that is already 1,000 times faster than the current state-of-the-art electronics nowadays. And not only we are stopping there, you can even go further by 1,000 times more. That's how you arrive to 1 femtosecond. So 1 femtosecond is 10 to the minus 15 of a second. And now we're talking about the real extreme limits where you have, the real extreme limits where you have here the time it takes for light to travel around the water molecule is at the order of an attosecond. So then now you have a feeling of what is an attosecond looks like. And now we will ask the question, why people talk about this at all? What is the meaning and demand of talking about this and doing research on this? And for this, we will go to the next slide. Why do we do attosecond at all? And why do we do attosecond science? And the question is answered very simply, just to investigate or to look or to study progressively faster and faster events. So if you go into the faster time scale, you start from protein motions, then you have proton transfer. Now you go down, you at around a picosecond regime, that's where you are probing rotation dynamics. And a little bit faster, you will arrive to the probing of vibrational dynamics. And remember, probing molecular dynamics is what actually gave the Nobel Prize to Ahmed Ziwel, so about 25 years ago. And that is not really the ultimate limit, because just few years after that, people show that it's actually possible to generate laser pulses that are shorter than 1 femtosecond. And because people can generate laser pulses with the duration shorter than 1 femtosecond, they can actually use this type of laser pulses to do light matter interactions, and therefore they can really probe what is called electronic dynamics. Now, you know by mathematics that if you really want extreme temporal confinement of the electric field, then you need broad frequency bandwidth. So roughly speaking, if you want a light source that is confined within 1 femtosecond, so less than 1 femtosecond, then you would need a coherent light spectral bandwidth more than 4 eV. So you need broad frequency bandwidth and you need coherencies. And thanks to nonlinear optics and the developments of the very intense laser pulses, these are actually possible nowadays. So that is the introduction where we discuss with you what is attosecond science, why we want to do this. And in the next part, we're gonna discuss with you historical developments. So please excuse me, because sometimes I have very basic slides, okay? So I hope you don't really feeling bored by this, but I think they are really nice, so that we also understand, the historical development, and we get the picture in a very realistic way. So a long time ago, you have seen about more than 100 years ago, so more than a century years ago, there was the works of Leonard Stanford and Edward Muybridge to answer the very simple questions. Do all the 4 hoofs of a trotting horse ever simultaneously leave the ground? So at that time, you know that there was no fast recording device, so that people can only actually ask and debate themselves a question without any proof. And soon later, Leland Stanford and Edward Muybridge developed what is called the very first applications of high-speed photography. And already at that time, they were able to take consecutive photograph at the order of 1 to the 25th of a second. And each of these photographs had the opening time or the exposure time of only 2 milliseconds. So that was really fast. That was already the record at that time. And just a side note, some of you may know that Leland Stanford sounds familiar to you, right? Yes, because it was exactly the millionaires that donated a large sum of money that founded Stanford University. So already at that time, about more than 100 years ago, people were already able to make it. But it took really a while for the modern technology to really develop and improve upon the previous existing technology and to make even faster and faster photography. And later they don't call it photography anymore, but they just call it a strobe photography. So some of the very famous works was actually done by Harrod and Engerton in MIT in the 1940s, where they really show that in the first time they could capture the picture of the bullet shooting through an apple. So you know that the bullet is extremely fast and human eyes cannot just watch it or follow the trajectory of the bullets, but camera can do. And of course, in order to do that, you need a collection of tools. But at that time, they was already able to make the time resolution a few microseconds. So compare to the technologies that have done in the very end of the 19th century, they were able to make about 2 milliseconds opening time. But now, after about half a century, they could improve it by a factor of 1,000 times more. And nowadays, it is very easy for you to see such a photo. I think you can see my mouse. It's very easy for you to see a photo because nowadays it is possible. For example, you will see that with the modern digital camera, and I just take here just a copy from the Sony's website. You see that for a very standard digital camera, you have the opening or the shutter speed at the order of 1/8,000 of a second, so it's about 125 microseconds. Well, that is the limit roughly for the conventional commercial community, not for the scientific community. And for the scientific community, it had been shown by the paper, I cited here the papers by my office PhD advisor, so Ferenc Krauss, when he wrote this review of modern physics paper in 2009, he already showed that at that time, building upon the works of Isaac Norris and Porter, they actually got a Nobel Prize also. I think they was working at MIT at that time. And they already were able to make a nanosecond time resolution at that time. But the real breakthrough was done by Ahmad Ziwei, not in the creation of the new laser pulses, but actually by the applications of the femtosecond laser pulse on observing chemical reactions. And that actually gave him the Nobel Prize. So that is quite quite some orders of magnitude. So in this case, it's around 6 orders of magnitude improvement in the speed at which people can observe the dynamics. And of course, sorry, yes, please.
I wonder about this quantum Zeno limit, like quantum Zeno effect. So if you go so fast, can you really say you observe it, or you do disturb it too much that you cannot really observe it? Because, I mean, if you say you observe some chemical reactions, but you shine some powerful laser on it, don't you change the chemical reactions?
You do. You do.
Okay.
But,
and to which extent?
But there is a catch. There is a catch. The catch is like this. Now it's different time scale we are talking about. So if you talk about chemical reactions, then actually you are talking about the time scale of, okay, let's say in this case, sub-picoseconds. Now, in this time scale, if you do the measurements, you do perturb the system. But you know that because of the time scale and the very high speed of your probing, you do enter the dynamic of your system, but the only visible effect of your alterations will only be seen afterward in another time scale.
So you're introducing some kind of disturbances, but they do not affect it right now, but only later?
They do affect it, but when you look at this, your observable doesn't really show the import. I mean, it doesn't contribute a high weight in your observable at that time scale. So, for example, when you talk about electronics, when you talk about electronic processing, then you are talking about nanosecond time scale. At nanosecond time scale, all the picosecond or femtosecond dynamics already finished long ago. And the only thing remaining is the final or the residual populations that is actually playing a role in your observable.
So your observation is taking much shorter time than the timescales you want to observe?
No. There are two time scales we're talking about. The first time scale is a time scale where we probe the system. The second time scale is a time scale where the result of the probing will be eventually, let's say, more visible to your detection. So imagine like this. I have a very simple analogy. You want to measure a motion of the truck. Now, what you're gonna do? Whenever you measure it, you kick the truck a little bit. But you know that the truck is actually heavy. So when you kick it, you do make the change in the truck motions. I mean, in terms of absolute numbers. But that kick is actually small enough so that you don't really see the effect at that moment yet.
Oh, because you make it faster, but the speed will show only in larger time scales, the increased speed.
So let's say like this, the total results of your observations actions is an integral that only be meaningful or largely observable at the longer time scale of your observation.
Okay, so going back to my first questions, your observations by laser is like the energy of that laser pulse is much smaller than the actual like kinetic energy of whatever you are observing.
Oh, no, that's another question. That is tough. Now, in our community, we have to be very careful with the photon energy and the time, the duration of the laser pulse. Because the photon energy will do different things. So if you come in with 1 femtosecond laser pulse, but the carrier wavelength in the visible domain, the effect is very different than if you come in with 1 femtosecond laser pulse, but the carrier wavelength in the XUV domain. Remember, I explained that in order to have sub-femtosecond laser pulse, you need 4 eV bandwidth. So you can have that 4 eV bandwidth starting at the center of like 3 eV at the center wavelength. You start from 1 to 5 eV, or you can start from 98 to 102 eV.
Mm-hmm.
So in both cases, you do have very fast temporal resolutions, but the photon energy will play completely different roles. So for the first case is where you have the visible pump or probe, whatever you call it, then you cannot do, for example, linear excitations to, let's say, noble gas or solid state system. I mean semiconductor, insulator system. But if you come in with 100 EVs carrier wavelength, also 1 femtosecond, you're gonna do a lot of things in a solid state or standard gas system. So you come in with the similar time resolution laser pulse, but the results will be vastly different depending on the carrier wavelength of your excitation.
Okay, thank you.
Thank you. Please, don't hesitate to ask me, okay? So I hope we can go on now. So at that time, actually, it was already after the very foundational papers. So they already knew that they could make observations way faster than what was the currently state of the art. So sub femtosecond, sub picosecond time resolutions. So before we go into more technical, more scientific part, I just want to remind you that, of course, many of you know already, but it doesn't hurt just to get reminded a little bit. The definition of a direct measurement. Why? For experimentally, it is very important that any measurements is nothing but a series of comparisons eventually to be traced back to the international systems of units. For experimentalists, it is very, very important. And because of that, then in our experimentalist eyes, there is no direct measurements, because any measurement that you're gonna do have to have a certain layers of comparisons, and then they will be traced back to the ISI system, to the SI system of unit. Okay. So now the important thing that for experimentalists we want to note is that how many layers of comparison you need in order to trace back your actually measurements to the ISIs. That is important because then, now, if you know that, okay, if you have a large number of n, so if n is like 10, so it doesn't matter if your layers of, if one measurement has 10 layers of comparison to the ISI and another measurement has 11 layers of comparison to SI, they are of the same level of directness. Okay, so this is the first thing. And second, now, if we look at the very simple picture, when we talk about observations, then the actual observation of our eyes, like the visual observation from our eyes, in terms of scientific perspective, it is nothing different than the capturing of the photo by a digital camera. Now, you see there are two routes over here, right? And if you call the observation of your eyes is a direct measurement, if you call it like that, then the action of you taking a camera is equivalently direct. But of course, from scientific perspective, I want to tell you, there are other routes too. There's not only just, just you have the photon arriving on your lens and your retina and your brain, but there are other ways to do that. And the other ways to do that, for example, optical spectroscopy, electron spectroscopy. And for us, from the scientific standpoint, they are almost of the same level of directness. Okay, so that are just some simple concept together with historical developments. And in the next, we're gonna discuss about the key technologies that enables the Nobel Prize in this year, as well as the foundational works to build attosecond science. The first is probably all of you knows already. So that was the Nobel Prize in Physics 5 years ago. And that was for the development of intense laser pulse, chuff pulse amplification techniques. In short, the idea of this is CPA, or the chuff pulse amplifications, is a technology that allows you to generate a laser pulse that is at least 1,000 times more intense than what you could have done without this technology. So I heard from my other scientists that whenever you could make any scientific contribution or technological contribution, you can consider engineering in this case, at the order of 1,000 times, so like 3 orders of magnitude better or improvement compared to current technology, that's where you get the Nobel Prize. So in this case, I just show you the simple graph where we show the CPA technology. But that is not only one technology that allows this. And the second technology is the developments in nonlinear optics. And one of the key examples is a generation of supercontinuum generations. So you know, by shooting very intense laser pulse on a given materials, you can induce either perturbatively or non-perturbatively the nonlinear dipole response of the mediums, and consequently, that nonlinear response will results in the emissions of the very broad frequency spectrum. And if you remember the slide we discussed before on the prerequisite for generating attosecond pulse, you really need intense laser pulses, and you also need very broad and broad frequency bandwidth. So let's coming back to here. In order to make really short laser pulses and eventually approaching sub-femtosecond like attosecond regimes, then you really need a broad bandwidth. And when you have a broad bandwidth, you may need the way to really manipulate them and then eventually combine them together to make it really short and cut back to the Fourier limits. And one of the ways to do that, that is to make supercontinuum generation and very intense light. So the supercontinuum generation that you have seen in 2 slides before was actually for like nano and microjoule laser pulses. But
there's a question.
Yes, please.
My question is, you need a broadband because when you go to Fourier transfer back to have the source time, right?
That's right.
Okay.
As simple as that. So that's maths. You cannot go, beyond that. So in order to make really short laser pulses, we need very broad and coherent light sources, right? And one of the way to have broad coherent light source and also intense is to use gas field capillary, and you come in with very intense laser pulse. And then with this gas field capillary, you would be able to make very broadband light. And you can see here, it's actually more than 2 octaves. And this very broadband light with more than 2 octaves would be enough to make attosecond laser pulses. And that would be in principle enough, but there is a challenge. The challenge is when you talk about the very broad frequency bandwidth, then of course you're gonna face the problems of dispersants, because it's obvious that different material or any material will react differently to different photon energies. So the problem of the dispersion becomes very trivial when you shoot in a very broadband lasers light pulse to a given mediums. Then they will emit at different moment in time or different phase. Now, our question is, okay, we could make very broadband light source, but in order to make attosecond laser pulses, you need to be able to bring them at the same moment in time. So you need to bring all the frequency components of that light source at the same moment in time. So you make to have zero phase or chirp free in that case. How you gonna do that? That was actually pioneered by my officer, PhD advisor, Ferenc Krauss and co-workers. So there was already a solution using the prism before. In order to compensate for the dispersion, you can use a dispersion also, for example, in the prism, but in the reverse way. Then you can compensate for that dispersion of the glass. Or you can use another technology which is called curved mirrors, and that technology can be shown here. So you come in with the laser pulse that is different in colors, you can see, but after they reflect from this mirror, they will be all in phase again. Then how does it work? The principle is actually simple when you think about this. Now it's obvious, but at the time, like more than 20 years ago, it was still in development. So that was actually a multi-layer mirrors. So the structure of each of these layers are actually engineered in a way that they allow reflection of different color at different depth of propagations. So by doing that, reflection of different colors at different depth of propagations, they compensate for whatever dispersion that caused by the previous media. And that's why after reflecting on such a curved mirrors, all the colors will come together in time again. That's it. So here we already cover most of the technology that allows us to generate attosecond laser pulses. And now comes the trains of attosecond pulses or isolated attosecond pulses. So let's talk about the key contribution. The first contribution is the generation of high order harmonics in gases. So high order harmonics, you know that in nonlinear optics, you can make second order, third order harmonics. But if you have the laser pulse that is even stronger than that, and you shoot on noble gas, what you're gonna see, not only second and third order harmonics, you're gonna make 20 and even more. And with the state-of-the-art technology, people were able to make 500 harmonics. So that is incredible, or even more nowadays. So An Hui Lei is one of the Nobel laureates of this year. Actually, also my intensive advisors in Lund. She contributed already for the very first works in 1988, and she here that she really show together with co-workers the generation up to 21st harmonics from intense laser interaction with xenon gas. Now, how do people understand that? That was understood by the paper of Paul Cockrum. So unfortunately didn't get the Nobel Prize for this year, so that I don't know. But I really believe that he's one of the pioneers in this field. There's no doubt about that. So he proposed the model which is called the three-step models. So if you have a very strong electric field coming, interacting with your noble gas, for example, in this case, then there is a moment where your electric field strength is strong enough to really bend the Coulomb potential together with the action of the electric field, right? Bend so much so that you allow tunneling to the continuum. And that is the first step. After a part of the electronic wave packet is turned out to the continuum, then it will be driven not only by the Coulomb potential, but actually more strongly by the surrounding electric field. And that step is called accelerations. And now if you remember the oscillation of the electric field, it is oscillating, so changing the signs every half a cycle. And because of that, there would be a moment where the electric field changes the sign from plus to minus. Then your electrons or your ionized, accelerated ion electronic wave packet may be driven back to the parent ions. And that step would lead to recombination, and all the kinetic energy accumulated during this acceleration will be released in the form of the XUV photons. So I will have the graphic to show you a bit better these pictures, but now let's go on to the key papers. So another key papers was a theory of high harmonic generation by low frequency laser field that was also together done by An Hui Lei and Paul Cockrum and co-worker. So Levenstein is one of the very famous worker in this case, and they propose what is called the strong field approximation, which is nothing but an approximation of the Schrödinger equation solution with the approximation that the electric field is too strong compared to the Coulomb potential, and therefore most of the dynamics is defined by the electric field outside. And this works allows the high harmonic generation process to be calculated quickly and accurately, and that is very beneficial, right? Because the moment you can calculate this accurately and quickly, then you can do a lot of study, predictions, and applications. Now, that was theoretical contributions, and then Agostini with co-workers then in 2001 demonstrated that by combining the attosecond pulse train, which I will explain a little bit later, with the laser pulse, they will have such a sideband signals over here, and these sideband signals will be modulated together with as a half of cycle of the driving field. And the oscillation of this sideband is the proof that they have successfully generated a trend or the consecutive and repetitive pulse, attosecond pulse. But that was not really isolated attosecond pulse, of course. So later, also in 2001, so Ferenc Krauss published a paper where they do very similar experiment where they generate the high harmonic first, and then they try to split the XUV and the IR pulse later and do the pump probe again. And at that time, because he couldn't have the carrier envelope phase stabilization, so the techniques I will discuss a bit later, so their streaking or their photoelectron detections looks a little bit blurry. But afterward, in 2004, now with the ability to really synchronize the electric field to be static in space and in time, then with this ability, they are able to show that they could make single isolated attosecond pulse. And with this attosecond pulse, they can scan the electric field. So now it is the first time that demonstrated that because you have the single isolated attosecond pulse, this pulse will be like a very sharp ruler or the detector for you to scan and measure the evolution of your electric field. And that's why they call it direct measurements of light wave, and why they call it direct measurement of light wave. So please remember, I try to give the reminder on what is the definition of a direct measurement. So in scientific language, yes, please.
So basically you show us how to create the attosecond laser, but how about the sensor? Is this like difficult to detect the attosecond time?
That's a very good question. So in this case, you don't see the direct signature of the attosecond pulse. You only see the electric field, right? Not the attosecond pulse. And now, in order to understand this better, we actually have a videos to show you how an actual experiment is done. And then from that, you would be able to see that, oh, whatever detection or observable you have already encoded a lot of information. Then you just need a proper theory and modeling in order to extract the information out. So let's start with our videos. So this is actually 3D rendering of our experimental apparatus where I did my PhD. So of course I didn't change this much after like 10 years. So in the beginnings, you will focus a very intense laser pulse on a vacuum chamber because you want to do it with gas and you want to control it very well, and XUV requires vacuum chambers. So when you have this, sorry, I want to be able to show the, I want to be able to control the, I cannot control the slide. It's okay. So here, if you look at this experimental chamber where you have the laser pulse coming into the gas target, and initially the gas target was actually not burned, but the laser pulse was so intense that it's actually burned the gas target. So imagine you have a tube, and then you shoot the laser in, and it's burned the two holes from the side of the tube. Then the gas will, be diffused out. Now, in the scale of the laser pulses, then all the gas and molecules are actually frozen in space because that time scale is too fast. So there's no absolute no movement of the atoms and molecules. So upon interacting with the strong laser pulses, your gas system will be polarized. How strong it is polarized depending on the strength of your instantaneous electric field. If the instantaneous electric field is very strong, then you can release an electric wave packet. And when the electric field changes sign, then it will be recolliding. It will be, accelerating and driving back to the parent ions. Now, in this case, because it has a lot of kinetic energies, so then all of this kinetic energy will be converted to the emission of the XUV photons. And that is the generations of attosecond pulses. Now, if you look into the coherent light source, so all your incoming light are coherent, so they come together in phase. So therefore, whatever emitted from your light-matter interaction are actually coherent in phase. So your XUV light is also coherent. So they are in the XUV domain and they are coherent, and thus are very good prerequisite to make attosecond laser pulses. And that is just the simple videos, right? So now we will show you the schematic. How do we detect them? Because, you know, from a scientific, experimentally standpoint, if you have not measured it, then you have not made it. And what we want to show you here is that the way how we can measure it. How do we measure it? We show you that by shooting in the gas on the neon target, shooting the laser pulse on the neon gas target, we can make XUV pulses. We can also have the IR pulses surrounding it. And now if we use some kind of filter to let only the XUV go at the center and the IR pulse going surrounding it, then we will shoot both of them on a dual component mirror, which means the inner mirror, the small mirror, the green mirror here, will reflect only the XUV, and the outer mirror will reflect only the IR. And now if this inner mirror will be placed on a piezo stage, so we can move it with nanometer precision, then with this geometry, we can do a pump probe measurements, which is nothing but a time delay scans of the interaction between the lasers, the IR, the XUV, and the gas, the target of your choice. And now if you put that on another neon gas target, so this is a target for the streaking experiment, this is a target for the high harmonic experiment where you want to generate the attosecond pulse. And here it is to probe. So this part is to generate attosecond pulse. This part is to probe attosecond pulse. And how do we probe them? Because we have the XUV light, so we probe them using electron time-of-flight spectrometer. And now by scanning the attosecond pulse along the time delay of the IR pulse, then we will measure the photoelectron spectrum of that. And the photoelectron spectrum of that will look something similar like this. And there you know that it is very clear or absolutely clear if you have an attosecond pulse, if you have a laser pulse long like this, and then you have an attosecond pulse, you scan through it, then this attosecond pulse will really give you a almost direct signature or encoded informations of your IR pulse. But not only that, the attosecond pulse will also be reflected or encoded in the shape and distortion of such a photoelectron trace. And by looking at the shape and distortion of this photoelectron trace, we would be able to extract the attosecond pulse also together with the IR pulse. So that is for the detection part. And we have shown that it is possible to do the pump probe between the attosecond pulse and the IR pulse, and their photoelectron signature would carry the exact information of the driving electric field, as well as a subtle information of the initiating attosecond pulse. And now let's talk about, we have all the technology, we have all the key papers, and now we will talk about applications. What are the applications? So we would have to say from our very humble opinions, in reality, because attosecond pulse are more or less the tools that are used for basic science. So we use this to probe really to push the limit of curiosity, how we can measure in an event in the fastest time scale. So that's the drive, the applications that most of the applications from this community so far was still in basic science. And one of the notable examples is benchmarking quantum mechanics and particularly the photoemission process. Now, when you talk about quantum mechanics and photoemissions, then you know that the solution of the Schrodinger equation, the photoemission, whenever you come in with high energy photons, then there is no time delay at all where your photoelectron will be generated, or in the other words, your generation of the photoemissions is instantaneous. But by doing this experiment over here, our colleagues show that, okay, the photoemission is by default instantaneous in quantum mechanics, but the observation of that is not instantaneous. And how does it come into play? Here we will consider the probing process of, in this case, of 100 EV light pulse. So you come in with 100 EV, roughly 100 EV attosecond laser pulses. You will pump the system. Now, when you come in with such a very high energy laser pulses, high photon energy laser pulses, then you will at the same time generate photoelectron from both the 2s and 2p orbital. Now that's a key point. You will generate photoelectron from both 2s and 2p orbitals. However, when you imagine when you have an electric field and you pump in, you generate the photoelectrons by your attosecond pulse, you have both 2s and 2p, okay? But you are gonna scanning it with your dressing IR. Now by scanning it with a dressing IR, you remember I showed you a few slides ago that with this, you can get the encoded information of the oscillation of the IR on the photoelectrons. So you will see that by looking at the upper trace, this upper trace is nothing but the encoded informations of the photoelectrons of the interaction between 2p orbital compared to 2s over here. Okay, so now the situation is maybe easily overlooked if you don't have attosecond laser pulse, but there is a key point. When you have a very good temporal resolution from the attosecond pulse, then you actually can look at how much these two traces, they look like the two electric fields, they look like the two identical electric fields, but in reality they are not. They look like identical, but they actually shifted in time. And by analyzing this shift, they recognize that it is at the order of 21 attoseconds, right? So that is critical because then this trigger a lot of interest from the theorists, because they were asking, okay, I thought it should be instantaneous, right? And then they do a lot of propagations, the TDSE calculation, and then they show that, oh, actually by the observation process or propagation in vacuum, you do induce such a observation-induced delay. And that is called delay in photoemissions, and that was only be able to probe by using such a very fast pump coming from the attosecond pulse. So that is one particular example. That's very notable examples. Another example is that actually you don't need to have at a single isolated attosecond pulse, but it's nice to have, is that you can probe real time. Yes.
We have a question.
Yes, please.
So, this energy resolution is almost few 12 or 30 electron volts, right? Almost 50 electron volt of resolution. Energy resolution of attosecond laser. But this energy scale is too large, right? It's electronic and solid state energy scale is almost less than 10 electron volt. Many cases. This only very hard to find the electronic dynamics inside of the solid is not easy, right? So this part is already solid state outside.
That's a good question. So let me try to answer this. I think you are absolutely true. It's absolutely right that we, in the beginning, we could only probe the dynamics of ionized electrons. because that was easier. But later there have been many other works showing that, okay, when we understand the dynamics of photoelectrons, we could try to put that and do experiment with more complicated system like solid, like tungsten, for example, or other multi-layer system. Then they can actually probe the propagation depth of the photons into different layers, and they will show up as a different delay in the photoelectrons signature. So they would be able to observe the dynamics from bound states. But of course, in the it will be, let's say, one layer less direct compared to the dynamics from continuums here. Of course, there are a lot of works already done in that direction, so it is right. And I just don't have time to show them here. But of course, yeah, the community now is mature enough to cover most of these applications. Another experiment we want to show you here is a real-time observation of valence electron motions. So this is not really requires a single isolated attosecond pulse, but it's a nice to have. And what happened is that if you do the very high energy photons experiment in a pump-probe fashion with your laser pulses, then of course you can also detect photoelectrons, or you can also detect photon. And when you detect photons in the transmission geometry, it is very easy for you. It's equivalent of doing a transient absorption experiments. This has been done long ago, like 30 years ago, long ago, or more than 30 years, 40 years ago in chemistry. But they, here, this, my former group just brought the whole concept to attosecond community, where they use the attosecond laser pulses. And then by using transient absorptions, where the krypton plus is only enabled by the arrival of the strong laser pulse. So then the XUV, by doing the delay scan with the XUV will be absorbed only after the arrival of the IR pulse, so that enable krypton plus. And then they will enable such a transition from 4p-1 to 3d-1. And now, interestingly, of course, you have here the spin orbit coupling. So then they will have a given energy gap. And now this given energy gap is shown as the modulations of the transient absorption signatures. And these observations will show as a quantum bit that you see over here. And this quantum bit is characterized exactly as corresponding to this energy difference here. And that's why, I mean, my former group, they claim that this is also another measurement of the valence electron motions. Of course, one has to come back on the definition of what is direct measurement and what is not. Okay, so I don't want to argue further into this, but from scientific standpoint, it is an interesting development. And of course, there's another works, not only by my former groups, by Anwile or Pia Agostini, but there are other groups like, for example, Mauro Nisoli from Milan, Italy. They also demonstrate isolated single attosecond pulses. And they use different technology compared to what we do. Using, in this case, they use this modulated polarization state. So this is just another technology behind, or in addition to our spectral filtering and amplitude filtering that we use in Max Planck in Munich in order to make attosecond pulse. So the field is now mature with a lot of tools, and some of the reasons record is that they could people could make about 40 attosecond pulses from the very similar concept, but putting a stronger constraint on the later pulses as well as the generation mechanism. So it has been done, and there is quite some application, but within the scope of this report, I would not be able to cover all of them. And next step, we're going to discuss about the prospects. So what is the potential future of this? One of them is actually done by my, of course, officer PhD advisor, so Ferenc Krauss, and in 2020, where he really shifted the focus of the whole division under his research from, guidance from attoseconds, the basic research in attosecond, to applied research, where they try to measure accurately the light-matter interaction, and from that measurements, they recover the information of the matter. And in this case, that matter is biological system. And they hope that if they are able to do this, if they are able to measure the electric field very, very precisely, then that measurement would tell them exactly all the information on the biological system. And one of the applications that he is aiming for now is the detections of cancer cells. But of course, that is a very long road, and this required a lot of effort and work. So this is an ongoing process. Another direction is that when the field is getting a little bit mature with gas, people start to turning solid, because that is where it is way more interesting. And high order harmonic generations now that serve as a basics of foundation for attosecond physics or attosecond science, but that was done in gas. And now people try to bring most of that concept to solid, and that has been done in the beginning by the group of Shambhu Gimire in Stanford in 2011, and then by the Regensburg group in 2014, and then our group in Gacking in 2015, and then there are so many other works. And just to summarize here is that I just copy the work from the Nobel laureates, right? Anything win lays if you hit it hard enough. So if we really try to shoot light, very strong light on the matter, you would be able to extract very fast and coherent light, and that is very good tool to probe the interaction itself. And one of the applications of such a works I'm going to show you here is the use of attoseconds high harmonic spectroscopy in order to study some very basic feature of the band structure. So that has been done, but that doesn't really require isolated attosecond pulse, but that is a nice to have. And for the condensed matter, the high harmonics spectroscopy is also important, because that may allow us to study other properties of condensed matter. So for example, like my other works here in ETS, where we show maybe we could retrieve the Berry curvature using high harmonic spectroscopy. And now we can also push beyond solid, where we can do high harmonic from liquids. So it's very interesting that we can show you the videos where we really have sorry. Okay, so where we have the solid target that is around 1 micrometer thick, and we shoot the laser pulse to that, you can see in the video here. And by shooting that here, we were able to generate also high order harmonics from the liquid, from the bulk of liquid. And that is interesting, because we really advance the high order harmonic generations and attosecond community from the gas phase that have been done about 30 years ago to 20 years ago. And for 10 years later, 10 years before, we start to move it to solid condensed matter, so including solid and liquids. And I would believe that there is a lot of promise in this community. And just a personal lessons I take so from this is my PhD defense picture with Professor Krauss. And he did once told me that success will only come to those who are prepared. So I thought that I read this from other people, and I remember this, but later, eventually I can cite it also from a Nobel laureate. So thank you very much for your time. And our group here, some of our works reported here are funded by various funding agencies, and we do have some position opens, and we do also have a company supporting the community. So thank you very much for your attention, and I'm looking forward if you have any questions.
Thank you, Champun. This was an excellent presentation. We are open for questions. Yes, Don.
So I wonder, do you always take just a snapshot of what's happening, like one picture, or can you take like a video of things?
Yeah. In time resolved spectroscopy, a video is nothing but a continuous snapshot at different time delay.
Yeah,
And
right, but then
we have done that.
Then you need to repeat your attosecond pulse very frequently, and also the thing that analyzes needs to be fast enough, right?
That's right. That's true. Yes.
So is it possible to do that, or?
Yes, we have done this. Yes, not we, let's say, other pioneers, they have done it before my time. I'm not claiming this. They have done it before my time.
Yeah, and a related question, when applied, for example, this to this photo effect, you say that there's a delay because there is an observation, which sounds like quantum Zener effect to me again. If you take like a continuous video, is the delay longer?
No, because our measurement is the scans as a function of the attosecond data pulse and the IR field. So this is a one complete time delay scan. And from this one complete time delay scan, we only learn one particular delay. We don't see that it is changing as a function of our scanning delay. We don't see that. Okay. There may be subtle effect to compare to with regard to what you have said, but maybe that subtle effect are not recorded in our measurements.
So what is the delay between different snapshots?
So let me go back to this because it is a little bit too fast to explain in one slide. So here. Now, let's talk about one particular delay, which is this, for example, this delay, okay? Then, what is this delay measurement? Is that we come in with the attosecond pulse, it generates photoelectrons, then from this photoelectron, it will see all the remaining electric field. Not the preceding electric field's half cycles, but all the remaining electric field half cycles. And then it will strict the final photoelectron energy instead of having exact. If you have a constant, let's say 100 eV and you have 21, then you will arrive with 79 eV for photoelectrons, but it doesn't. Because of the stricting up and down of your remaining electric field action on your photoelectron, it will be shifted to a given numbers, for example, to this point. I don't know if you see my mouse.
Yeah.
So to here, okay? Now, so then when you do the photoelectron, you actually do the time integration from the moment the attosecond pulse comes to all the remaining time afterward of the laser pulse. Then from that, you get only one photoelectron spectrum.
Oh, I see.
You move this delay of the attosecond pulse to another position, then you're gonna measure all of this from here to here back again, and that will give you another photoelectron spectrum over here. And now you see that, okay, by doing this scan, you actually see the effects of the electric field up and down, right? On the generated photoelectron. It's going to be strict up and down in kinetic energies. So then it means that this scan will give you only one trace. One data here will give you one photoelectron here. One data here will give you one photoelectron trace over here. And for this complete scan, you're gonna see this complete trace. When you scan this, you're gonna see complete trace. But this, what is called streaking spectrogram, show not only for one photoelectron, but for two photoelectron, because two of them are generated by 2s and 2p under the same 100 eV photons. So they are generated under different kinetic energies. So each of them will be modulated up and down within their own center of mass kinetic energy, which is this, which is here and here. And by looking at them, they look almost identical, but they are actually not. And the subtle difference between their striking spectrograms show the attosecond resolution time delay.
Thank you.
Thank you.
Do we have any other questions?
I have a very technical question.
Yes, please.
When people model high harmonic generation, theoretically, they usually retrieve the emission spectrum in the experiments from the dipole acceleration.
That's right.
And I could never, when you look at the dipole acceleration from ground state atomic samples, the high emissions happen, they happen because of high harmonics that actually take place when the field is at its maximum, which is when the electron is further away at the quiver radius. And I could never understand how this is related to the recombination step, because if you measure, if the emission of high harmonics is theoretically obtained from something that happens when the electron is far from the atom, why is this describing the recombination in the experiment? So I don't know if my question is, essentially, if you have to formulate this question is in one sentence, is why does the dipole approximation describe the emission in an experiment? What is the relation between the measure and the dipole approximation?
So there are two things we want to discuss here. First is electric dipole approximation. It is quite a different things, but it's very relevant because in order to solve the Schrödinger equations, we have to apply a given approximation. And in this case, electric dipole approximation is totally valid because we are using the wavelength that is much longer compared to the ball radius. So electric dipole approximation is certainly valid. Second, we talk about strong field approximation, or in the other word, roughly assuming the electron traveling in continuum can be described semi-classically. And for that, I have here the simple graph show you. I hope it is a bit clearer now. So I made here the very simple code. You know, this is just a Newtonian mechanics. So if I have a oscillating electric field, and now if the electron, if it is emitted at this moment in time, then the classical mechanics will say that at this moment in time, it will likely recollide back at the same coordinates or x coordinate as the beginning. So it means that if it is emitted at this time, it is likely recollide back to the parent ion at this moment in time. And the trajectory it goes is that it can go up to, you can see here, it is this blue curve, dark blue curve, is go up to like more than 3 nanometer. Totally classical. Okay? And if you have electron emitted at this moment in time, so then it will take a very short trajectory. So it will go very nearby the core parent ions, and it will likely going back to the same positions at this moment in time. So this is a very short trajectory. So this is called very short trajectory. And with this approach, you will see that classically you do have the chance or probability to the electron to recollide back. In order to solve it better, you would have to use 3D TDSE integration, so that you will have the more exact probability density probability, but that is very low. It is shown that by experiment that the efficiency of the total high harmonic process is very, very low. And that is a bottleneck preventing this high harmonic process to be a next breakthrough that totally transform our life, because it could not replace XUV, incoherent XUV source in the lithography for modern electronics. It could not so far. If it could, then it will totally change our life.
Thanks.
Thank you.
Okay, any other questions? Seems not, so then let us thank Tran Trung again.
Thank you very much for your attendance and the questions. I appreciate it, so it's my pleasure. Just let me know if is there any further or follow-up question. I would be glad to discuss with you, or potential collaboration. If you have any ideas, we would be very happy to hear from you. So just drop us an email. We are experimentalists. We can tell you what are the tools we have. If you have any ideas, and our tools are there, it will be very fast to do. Thank you very much. Have a good day.